Hello students, welcome to the lecture on materials for coastal projects. In addition to watching this, I recommend you click through the lecture because I will not be covering all of the points covered on the slides. So the main topics we're going to talk about today are material properties, different types of materials, specific materials that we're going to use on coastal projects, and how to design and select from those materials. Specific gravity, or also sometimes called specific weight or density, with slightly different units, is a very important property near the coast. Specific weight needs to be greater than the specific weight of water, or else a material is likely to float when it is inundated with water. So during tsunamis or other events where the water level becomes much higher than anticipated, it's even possible for a building to float away due to not enough specific weight of the material. Strength is a material property that needs to be given great consideration and is basically just the amount of stress that a material can withstand prior to breaking. Near the coast, it's important for materials to be able to resist cyclic and seismic loads due to the cyclic nature of waves and the likelihood that a coastline is near an earthquake fault line. It's also important for materials to be flexible, to be able to bend without breaking, and for whatever materials you choose, for them to be compatible with one another. For example, for you to choose two metals that are either going to intentionally have one be sacrificial and corrode and the other not, or have them not cause inadvertent corrosion on each other. Additionally, it's important for a structure to be durable for obvious reasons, so it lasts a long time, adaptable, so you can change the structure if needed. Cost is always a factor in every project, and available materials is an important factor as well. Here's a list of various materials that we're going to talk about further in the next slides, as well as an animation. I encourage you to watch it. It's pretty cool. It shows you how a breakwater might be constructed using construction equipment and various materials, as well as there's a Google Map link to that actual location of Port City, Sri Lanka, for you to check out if you're interested. Earth and sand, also known as dirt, is a very important construction material. We're going to talk about it in later lectures as well, but for now, one important point to emphasize is that water, the amount of water in the earth and sand or the soil, plays a key role in the strength of that soil. We'll discuss more later. Here's a list of different structures that earth and sand may be used as a fill material for, and then a video to watch on Chinese islands that are being built in the South China Sea using earth and sand as a fill material. Here's a video I'd encourage you to watch that dramatizes the world slowly running out of sand, while at the same time giving you a picture of what goes into dredging a beach and why a project like that, also known as beach nourishment, would be undertaken. Another coastal construction material we're all familiar with is stone, used in many types of different, for many types of different purposes. Here's a picture of a few different jetties and seawalls that are being built with stone. And then the one on the far left is interesting to look at because you've got some ropes that are tying in the rocks. And so those ropes are helping prevent erosion, similar to what geotextile does for sand, which we'll talk about later. This slide shows different characteristics of stone. A couple columns I'll highlight is the compressive strength column. You can see for granite, for example, we're talking 100, 200 megapascals, whereas if you go down to chalk, bottom of the sedimentary column, you'll see 5 to 30 megapascals. So a big difference between granite and chalk, and variation in compressive strength amongst rocks. Another column I'll highlight is the porosity column. Again, if you look at granite, it's 0.4 to 2.4%, so pretty small. But then if you look at chalk, it's 20 to 30%. So that's how much, that's the ability of water to flow through it. So big variations in different types of rock. This chart shows the variability and durability for different types of rock. At the top, you see granite, and at the bottom, towards the bottom, number 7, sandstone is one you're all familiar with, not very durable. It's always important to consider the environment and how it affects your construction material, and stone is no exception, especially because it may have small cracks naturally already started. And so if water gets into a crack and then it freezes, the freezing strength of water actually exceeds the compressive strength of many rocks, and so it will cause it to crack. So that must be taken into account when choosing it as a construction material. Steel is an important construction material both on land and next to the water. The top photo, you can see a seawall being built with some steel, and then at the bottom you can see some caissons being built with steel as well. Note that both of the steel are already orange in color, so they've already started rusting. So this is just something you have to live with and plan for in the marine environment. Ceramics are a very useful engineering material in that they're very high strength and they're good insulators, even at high temperatures. However, they have low toughness, so that sometimes can be a factor, meaning they're quite brittle. Composite materials are just defined as being a material composed of two or more different bonded together. Some examples of composites are the Dreamliner fuselage. You can see some fiberglass airfoils in the top picture. You can see the DDG 1000 superstructure to keep the lightweight at the top. And then also I'd encourage you to click on the Rapid Runway Repair link. You've got some uses of composites there. But by and large, the main advantage of using composites is they're often light and they're strong, so they have a high strength-to-weight ratio. Here's a picture of a couple sailboats. Due to the high strength-to-weight ratio, they're often used in high-performance hull design as well. Wood, which we all know and love, is a natural composite material. It's made up of both cellulose and lignin. Cellulose is the soft part of wood. Lignin is the harder part of wood. But the definite advantage of using wood is that it's renewable, it's easy to work with, it's cheap. But some of the cons you can see in the bottom picture, you see the barnacles and different deterioration of the wood over time. Additionally, a consideration for wood is that it's not isotropic, meaning that it doesn't have the same properties throughout the wood in any direction. So you do have to take the grain direction in consideration as you're constructing with wood. Here's a picture of a couple different coastal structures built out of wood. And you're probably not surprised to hear that different woods have different characteristics. At the top you see softwoods, at the bottom you see hardwoods, and you can see the three rows in both of these are shrinkage and volume from green to over dry or oven dry. So that's from when you cut the tree to when you've fully dried out. You can see a range from anywhere from 3 to about 18% shrinkage there. Modulus of rupture is another name for ultimate strength for wood. You've got all those listed as well, and then also modulus of elasticity, which you're familiar with for metals. The same thing is true for wood. Concrete is a very common construction material, and we're going to cover it more in a future lesson. Here you can see a concrete bridge, concrete barge, and then actually a concrete ship. A definite advantage of concrete is that it's good in compression, meaning it's strong in compression, and that it's durable. It's hard to break it, hard to get rid of it once it's there. Con of concrete is that it's not strong in tension. So the tensile strength of concrete is actually about 1/10 the compressive strength of concrete. So that definitely needs to be mitigated when you build a large structure out of it, expecting the structure to be strong. Polymers are another common material. In the bottom left, you can see some nylon rope. In the right side, you can see a rubber tire. Big advantage of polymer is that it's flexible and that it's corrosion resistant. Here's a couple pictures of geotextiles. These are used to withhold sand and prevent it from eroding near the coast. Here's a picture of a couple of geotextile bags, also known as sandbags, and they do an excellent job of preventing erosion near the coast and providing structure to prevent inundation of water on the coast. Pro of geotextile is that it's easy to place, but definite downside is that it's difficult to repair. Once the fabric breaks, it's hard to repair without fully replacing the bag. So now that we've learned about some of the different materials, when selecting the materials, you got to base your decision off of all these characteristics listed, many of which we've already discussed. And some others to consider are the appearance. So sometimes your customer actually cares how it looks. So if you're building a seawall at a city, such as the New York City Manhattan project that's currently being worked, it's very important how it's going to look, whether it's aesthetically pleasing, and also whether it's sustainable, or whether it's going to help or hurt the environment. Another perhaps obvious consideration is the lifespan. So most structures, obviously you want it to last as long as possible, but sometimes you don't really care. For example, as an H-60 Romeo pilot, I've shot out a lot of sonobuoys for my aircraft, and those are only supposed to last at most 8 hours, and then they sink to the bottom, never to be used again. Constructing a sonobuoy would vary greatly from constructing a permanent buoy on the coast that needs to last for years and years. In review, we've discussed a lot of properties of engineering materials. We've talked about the different uses for them and how you might select them if you're designing a project.